Hello everyone, my name is Burak Uskent. I will present how we perform dynamic inference on grounding-based vision and language models. This is a joint work between myself and my co-authors at Amazon Prime Video. MDETR is one of the recent vision and language models that can perform well on grounding-based downstream tasks. However, it contains large number of parameters which increases their runtime complexity. To mitigate this problem, we propose a dynamic inference approach on the MDETR model. We can see our architecture in the figure. We insert decision networks to learn to skip multi-head self-attention and MLP layers in both vision and language backbones. Additionally, the decision networks learn to prune the token dynamically for the vision and text backbones. Finally, we insert another decision network in the multi-model network part, where the goal is to dynamically skip MSA and MLP layers. Grounding-based vision and language models are pre-trained on text condition object detection task. The task is to detect all the objects mentioned in a text query. MDETR and GLIP models can be considered as the most recent examples of them. GLIP, different from the MDETR, uses transformer backbones and it does not employ multi-model transformer. Instead, it performs fusion in between the backbones. These models can perform well on downstream tasks that require grounding. On the other hand, they contain large number of parameters, and this increases their runtime complexity. In this study, our goal is to mitigate this problem of the grounding-based vision and language models. We built our dynamic inference on the recent MDETR model. In this direction, we replaced the CNN backbone with a VIT backbone. This way, we can dynamically skip MSA and MLP layers across the vision and text backbones, as well as the multi-model network. Additionally, we can perform dynamic token pruning on both vision and text tokens to maximize the drop in the runtime complexity. Here we show our dynamic VIT MDETR in details. First, decision network takes vision and text representations from the backbones and provides actions for MSA and FFN layers, skipping and token pruning for the following blocks of the vision and text backbones. We insert several decision networks across the two backbones to reduce the burden on each decision network and to fully cover all the blocks of the vision and text backbones. Finally, we insert another decision network to dynamically skip MSA and MLP layers across the multi-model network. We note that we are not doing token pruning in this part, as we already did token pruning for vision and text backbones. We want to note that multi-model network consists of encoder and decoder components. Next, we explain how we perform optimization using reinforcement learning and knowledge distillation. Decision network for the backbones is represented by F sub D, and it takes the representations Z sub V and Z sub T from text and vision backbones. We pass the output through sigmoid layer to get predictions between 0 and 1. Decision network outputs predictions P sub P and S sub P. They are converted to binary actions A sub P and A sub S, where A sub P represents the actions for vision and language token pruning, and A sub S represents the actions for vision and language MSA and MLP layer skipping. On the other hand, the decision network for the multi-model network is represented by F sub M, and it outputs predictions S sub F, which is converted to A sub M, that represents the actions for MSA and MLP layer skipping in the multi-model network. Our objective for the decision networks have two different components. The first one includes the reward for the backbones, and the second one includes the reward for the multi-model network. On top of them, we use the policy gradients algorithm to optimize this objective with respect to the decision network parameters theta D and theta M. And our objective for the model includes linear combination of task loss and knowledge distillation loss. For knowledge distillation, we use the fixed network's predictions and representations to optimize the dynamic model. In this case, the fixed network is basically our VIT embedded architecture. Finally, we perform experiments on 3 different vision and language tasks that includes referring expression compression, visual question answering, and referring expression segmentation. For referring expression compression, we use RefCoco, RefCoco Plus, and RefCoco G. For visual question answering, we use GQA. And for referring expression segmentation, we use phrase-cut dataset. In the table, we can see that our method can maintain the accuracy of the embedded and glib without a major loss while improving their runtime complexity by 50%. We note that our model contains similar number of parameters to embedded and glib models. On the left side, we can better visualize the improvement in complexity. Next, we analyze the learned actions by the decision networks. Across the vision and text backbones, the probability of skipping the MSA and FFN layers go up with respect to the depth, as shown in the figure at the top. On the other hand, as shown in the figure at the bottom, there is not a specific pattern in the multimodal network's encoder and decoder parts. Finally, we analyze the learned policies qualitatively. At the top, we have relatively simple image and text pairs that are assigned similar policies. On the other hand, at the bottom row, we see relatively difficult image and text pairs with similar assigned policies. This shows that types of policies learned by the decision networks have correlation with the difficulty of the input image and text pairs. With this, I would like to conclude my presentation. Thank you very much for listening, and I hope to see you during our poster session on Tuesday.